So welcome to Introduction to Blockchains. Everyone aboard the hype train, choo-choo. You can find these slides at slides.myname.me/introduction-to-blockchain.html. If you go to that slides.lucywyman.me, there'll also be a link there, so it's a little easier to remember, just the slides website. And let's rock and roll. All right, so in this talk, I'm going to cover what blockchains are, how blockchains work, when you should and should not use blockchains, and a framework for determining if blockchains are right for your use case. And then we'll talk about how people are using blockchains now for uses other than cryptocurrencies. This talk is not focused on cryptocurrencies, but cryptocurrencies do often come up in examples and are where a lot of these ideas and technology are based. So it's not a talk about cryptocurrencies, but also I might say Bitcoin a lot, and I apologize. Okay, who am I? My name is Lucy. I am a software engineer at Puppet. I work on an open source tool called Bolt, and basically look like this pretty much all day. I asked my friend to take a video of me working. All right. Okay, so let's start off with what is a blockchain. And in order to explain what a blockchain is, there are a couple of key concepts that we need to cover first. So that first concept is a hash function, not to be confused with a hash object. Ladies and gentlemen, your first overloaded term of the talk. So a hash function has a couple of nice properties. It takes input of any size and outputs a fixed-sized string. So basically, no matter how big or small my input is, it will always have the same size of output. In addition to that output being a fixed size, it's also relatively unique. Obviously, the input space for this function is much larger than the output space, so there will be what we call hash collisions. But for modern sophisticated hashing algorithms, and especially when we have meaningful data input, so input that's not just random, collisions are very rare, and we can pretty much guarantee that our output is going to be unique for a given input. They should also be idempotent, so this means that no matter which system I'm on, no matter what time of day it is, no matter where I am geographically, given the same input, it should always output the same thing. So yeah, that's it. Given the input A, B, C, D, it should always output E, F, G, or whatever, no matter what. And we can rely on that. And the last really nice, attribute of a hash function is that you cannot invert it. So you cannot determine what the input was given just the output. So I can't reverse engineer it, so to speak, or can't know what the input was if my only information is the output. You can definitely learn more. Hash functions there's whole university courses on this topic, but I think this is all you need to know to understand what a hash function is. I have a little example here. So I have this hash function that I'm just calling in a read-eval print loop. So we see there's two differently sized inputs, and the output is just a base 64 string. Yeah. Okay. So public key encryption is the next idea that I think is key to understand when we're talking about blockchains. So with public key encryption, this is also called asymmetric key encryption, is another common name for it. I have two keys. One of them is public, which as the name suggests, means that anyone can see it. And the other is private, which as the name suggests, means that no one else except for me should be able to see it. Anyone can encrypt a message with my public key and know that I am the only person that can decrypt that message using my private key. Or another nice feature of public key encryption is that I can sign my message with my private key, and anyone can decrypt that message with my public key. So basically, it gives me a way to securely communicate with people and verify that I am the only person that is sending and receiving those messages. It's a lot more complex than that, similar to hash functions, but because of the mathematics behind this, specifically like elliptic curve cryptography, we have a very high degree of trust in public key encryption, and it's used pretty widely throughout like any communication protocol. So like SSH, my like browser connection right now, I think uses some form of asymmetric key encryption. And we can have a very high degree of trust that as long as I'm the only person with my private key, it is definitely me giving and sending those messages. And again, there's way more to learn here, so definitely check that out. The only other thing to note in talking about public key encryption, especially if you're like brand new to the cryptography space, is that oftentimes when people talk about blockchains, they will include public key encryption as like the first thing that they start explaining. And public key encryption and blockchains can be used together, but they are entirely separate technologies. So do keep in mind that if you're reading about elliptic curve cryptography or ECDSA or anything like that, like you're actually reading about public key encryption and not about blockchains. Okay, so with all of that preamble, let's talk about blockchains, what you came here for. So a block is just an object, so it's a thing that has attributes. There are three main attributes that it has. The first is a cryptographic hash function. So again, that hash function we were talking about, but it's cryptographically secure. So a regular hash function is just taking any size of input, making sure that the output is the same size. The cryptographic hash has that nice property of making sure that it can't be inverted. So everything we talked about, cryptographic hash function. So we are applying that hash function to the entire previous block in the chain. And this is kind of the secret sauce of blockchains. This is where the magic happens, is I am storing in my block a string that represents all of the data that was in the previous block. All right, we'll get more into this later, or like we'll keep reiterating it more like, but like this is it. This is the blockchain. We also store a creation date timestamp, so most chains will be just chronological in order, so we want to have a timestamp. And then we can have some sort of data. And oftentimes that data will include the block like owner's public key that we were talking about, so that indicates some kind of ownership of the block. But that isn't necessary to have a block or have a blockchain. So your data can be pretty much anything. Typically, it's transactional because your block is acting as kind of a ledger of sorts. So it's basically, think of this data as being immutable. It's not going to change. But the data can be really anything. It can be how many cats someone has. It can be data about who you are, anything you can think of, what color your hair is. Okay, so here's a little example of the blockchain structure. I have a Git repo, github.com, my name, blockchain-example. This is just demonstrating the structure of blockchain. It doesn't demonstrate like the networking or anything like that. But we can see I have that timestamp. I have my data. I have included the previous hash. So that's the hash from the last block. And then I've also included an index, which just indicates where in the blockchain this block is. So that's like, a blockchain is a list. If I have 0, 1, 2, 3, and this is like the fourth block, then that index will be 4, for example. So I have where the block is in the chain, and then some data. And then I also have the block hash itself. And this is just for an extra layer of verification. And we'll see an example of that a little bit later. OK, so we understand what a block is. but it's called a blockchain. So what's this like chain part? Oh, and my example is in Ruby, but there are tons of other much more fleshed out examples of really simple blockchains in pretty much every language you probably like. This is not a complete list, but yeah. Okay, so what makes these into a chain? We already talked about that like previous hash part. So the chain is just a data structure. I think of it as just a glorified linked list, but it only has the append function. So I can't actually modify the data in any of my blocks, but I can add more blocks to the chain. The reason that I can't modify any of the data in my blocks is that if I change the data in a block, then the hash of that block will change. And if the hash of that block changes, then that previous hash value in the next block won't match what the actual hash value of the block is. So there will be a discrepancy in the hashes of the block and the previous hash I have stored in the next block. So then I would have to rehash the next block as well, update the previous hash in the next one, rehash that, update, rehash, update. And by the time I did that, even more blocks have been added to the chain. And so it is computationally not impossible, but infeasible to modify any data in the blockchain once it's sufficiently far back. Someone raised a hand, yes.
The hash function of the block is based on previous blocks, not just data, but also cache.
Yes, yeah. I'll show you an example in like 2 minutes. And yeah, this is probably not the last time we'll discuss like the hashing chain, but yeah, does that, sorry, before I move on, does that make sense to everyone a little bit of the, if I change a block, then the hash looks different and I have to rehash it? Cool. Another attribute of blockchains is that they should be decentralized / distributed / public. This is not inherent to the like technical data structure of a blockchain. So you can have a blockchain that is not decentralized or distributed or public, and it is essentially just a linked list with only the append function. But in order for it to be a blockchain, or to be considered a blockchain within the community, I should say, it should exist on multiple nodes. And the thinking is that anyone who can write to the blockchain should have the ability to also read from the blockchain. And so you can think of a blockchain as being a distributed digital ledger. This is a good just like forward. Someone at a cocktail party asks you like, hey, what's a blockchain? You went to that talk, right? You can say, it's a distributed digital ledger. Although admittedly, when I'm at cocktail parties, I usually talk about a different type of ledger. This is Heath Ledger, for those that don't know. Okay, so here's a handy visualization. So yeah, here's a good way of like visualizing that like hashing linking we were talking about. So each block is linked to the previous block. That's what a linked list indicates. And the link is that I'm storing both the hash of my block and then the previous hash in the next block. So yeah, and then you can just imagine this goes on forever. All right, I see people taking pictures. Yes?
Is it just the hash of data, or the hash of the entire block?
So it's the hash of the entire block. The hash of the entire block does not include the hash of itself. So it's not, so it's going to be a hash of the index, timestamp, data, and previous hash. But I obviously can't like hash my own hash. Yeah. Usually what this ends up looking like is just shoving everything into a string, like concatenating all of those values and then doing a hash on that. I don't actually know how like production blockchains do it. Like I'm not sure what this looks like for Bitcoin. But for my little example one, I just like, yeah, print everything to a string and then hash that. But yeah, as long as the hash or the previous hash value in block 1 is part of what's hashed. I think that's really the key part, is what you don't want to, and basically anything you want to make sure isn't changing should be hashed. Okay, so coming back to my blockchain example, so here's what the blockchain object looks like. It's just an array. I instantiate it with a first block that has basically like 0 information in it, so it's like all zeros and nils, and that's because there is no previous block to hash. So I just want it to be kind of nothing. And then I have an add block function. It increments the index. It gets the previous hash from the last block. It gets the timestamp. It has some data. I make a new block, and then I just add it to the chain. And the example, I actually forgot to update this slide. Whoops. But in my example, I'm using a blockchain to count ballots. And this is a real use case that has been talked about being used, is using blockchains to record votes and then like count them in a way that is more publicly visible and where people can track like where their vote is going and verify that like their vote doesn't change. And that is to inspire trust in people's votes, not just in America, but like around the world. Okay, so let's take a look at that in action. So I have a couple of files here. I have my blockchain, which has those 2 objects. And I also have, so here's that like toString function I was talking about. Makes what's called, in Ruby it's called a here doc, but it's just a long string of all my data. And then I have my hash function. This is just calling the like Ruby library of hashing. And then down here, I have my blockchain. It looks just like it did in the slide. And then I also have this verify that a block hasn't changed function. And this is doing 2 different checks. So it rehashes the block and makes sure it matches the previous hash value in the next block. And then it also makes sure that my hash value hasn't changed. Because again, we can't like hash our own hash. And so I just also check that the hash hasn't changed and that it matches the previous hash of the next block. So kind of making sure that everything is square. And then I have this little example script. So I make a new blockchain. I have a list of people who are going to vote. I make my first block in the chain, and then I have everyone get added to the blockchain. So everyone submits their vote, and then I print the entire chain. So I'll print each block, all of the data in the chain, and then I also call that verify function to make sure that I voted. Okay, so I'll run that example script, and we can see that here's the first block, and here's the hash of the first block, and we can see that that matches the previous hash value in the next one. So there's like kind of the link. And then similarly, my hash value here matches the previous hash value there, etc. Yeah. All right. Pause for questions. Yes?
As the chain gets longer and longer and longer, is there a chance that it would get so long it would be longer than the hash? Or does the size of the hash have to grow if the chain gets super big?
No, the hash always stays the same size. So that's a property of hash functions, is that no matter how big your input is, like I could call this hash function on the entire like Moby Dick book or something, and it would still output a hash that is this size. So yeah, the output string is always the same size no matter the input string. And yeah, yes?
How do you handle hash collision?
Good question. You don't, basically. Like, if there's a meaningful hash collision, so like Git is actually a good example of using hashes. Every commit has a hash. I think that so far they've had 1 collision, I want to say. And it was just a matter, it's a people thing, right? So it kind of depends on the use case, and like people just have to sort it out. We basically can count on there not being hash collisions. Yeah, yes?
Is the index problematic or a distributed system?
No, because, well, kind of. We'll get a little bit into consensus algorithms and like the distributed system part. But basically, all nodes in the network should have the same blockchain, the same authoritative chain. So there exists one true chain, and that is what the so yeah. Since there's only one chain, the index is not an issue. Does that make sense? We'll get into it. Let me know at the end if I haven't answered your question. Yes, we will cover it. Yeah, yes.
So you're saying that you can't hash a hash, but if you use an input string, I understand why you would want to, but what is preventing you from actually hashing the previous blocks?
Oh, so you totally can. I just can't. What I meant by that is that in theory, this hash is like the hash of my entire block, but since the hash is like within the block, I can't have this hash like hash itself. So if I call the hash function on all 5 of these attributes, then the hash would be different than this, and it would be like, well, what is hash? Yeah, does that make sense? Okay, cool. Any other questions? Ooh, yes, red shirt. Not that I know of. Bitcoin right now is like 45 megabytes, so, and growing. Yes. I'm sorry, say that again.
Can you encrypt the data and then have like a binary string that then gets hashed?
Yeah. Depends on like the language you're using, I think, but yeah, ultimately it's like a bit array that gets hashed. Oh, it does not have to be public. Like that's just a like social decision you're making. So that's oh, excuse me. That's not like part of the technology itself. So that is like a decision you can make. There are private blockchains. You can have blockchains where the data is encrypted and no one can see it. You can have blockchains where some of the data is encrypted and no one can see it. You can have blockchains where only certain people can see it and it's permissioned. So yeah.
But you can still hash, right?
Yeah. You can still hash it, yeah. Yes.
You told that the previous hash is hash of previous
Say that again. No, it's a hash of, yes.
In this case, why do you hold before that we cannot change value because the hash
Because then the previous hash value will change.
regardless of that?
Yeah. All right. Oh my God, really? Okay, I'm like running way behind on time. Oops, sorry. Okay, so how do blockchains actually work? In order to add a block, we submit a transaction. We generate a block for that transaction. In the case of most production Bitcoins, what actually happens is that blocks are bundles of transactions. So my transaction will get like put into a block along with multiple other transactions, and then waves hand. The network determines if the block is part of the authoritative chain. Okay, so this is where things get a little like interesting, we'll say. So the network part of this is an important part. This is like why decentralization is really cool, is because it's an algorithm or a network of people determining what is and is not part of the chain instead of like one authoritative figure. So part of the nice thing about decentralization is that it removes like a central authority that can tamper with the data. Okay, so someone asked about what happens if I have 2 writes on 2 different nodes at the same time. So I basically have 2 different correct copies of the blockchain. Like, how do we reconcile that? So we reconcile that by, it's called the higher value chain, although what does higher value mean? Is a very interesting question. So there are a number of what we call consensus algorithms. So that's basically how we choose one chain over the other. All right, I'm gonna take a little topic branch, but I promise it comes back around. So another thing that we want to prevent when we have a blockchain is people adding blocks to the chain that they have stored and then saying, oh, this is the real blockchain, when they didn't do work to add it to the blockchain, when it's not a valid list of transactions. So we want to encourage good actors and discourage bad actors. And in a network situation, this is called the Byzantine generals problem. So it's ensuring that you want to have as high of a tolerance, oh my gosh, excuse me, as high of a tolerance for bad actors as you can. Yeah, and this means that you are Byzantine fault tolerant. Because blockchains are on a network, we want them to be as Byzantine fault tolerant as possible. So because of this, we have chosen a consensus algorithm, or the most popular consensus algorithm, I should say, is called proof of work. And I'll go into more detail of how proof of work works, but basically it makes it impossible for bad actors to try to add a malicious block to the chain. So they can still submit malicious transactions in theory, although with the public-private key system, that is also very difficult. But in order to take over the blockchain, so in order to say, no, my block is part of the chain no matter what you say, I would have to have control of 51% of the network, which at this point in time, for Bitcoin, for example, computationally, that would cost $6 billion, I think. So the way that proof of work works is it chooses whichever chain has done more computational work. And the reason that this is successful is because computational work is expensive. It costs a lot of power and means that it is very hard even to be a good actor, but also to be a bad actor. The only problem with proof of work is that it is not very environmentally friendly because it is consuming so much power that has severe environmental consequences. So other consensus algorithms are being looked at. Proof of stake is a relatively popular one, although there are still some technical problems with it that need to be solved first. Okay, this is my proof of stake. It's Nick Offerman hitting a stake. So when we have two blockchains, we use a consensus algorithm to choose one of them, and then the other blockchain, the other block that was being proposed to be added to the chain just gets orphaned and is not added to the chain. So in practical terms, usually the transactions that are bundled in that block just get added to the next block that gets added to the chain. So it's not like you go to buy something with your Bitcoin and you just can't buy it. No, the transaction just gets added to the next block in the chain. But that previous block, the very first block that your transaction was a part of, is just not part of the chain and eventually just gets dropped off into the ether. It's called an orphaned block and it just goes away. It gets overwritten by the authoritative chain that is decided. Yeah, does that answer your question? Cool. Okay, so diving a little bit more into proof of work, because it is actually pretty interesting. I know that this image is probably not big enough to see, but if you have the slides up, I highly recommend clicking on it and figuring it out. So in our block structure, we have an attribute that's called a nonce. This is just a 32-bit number. Usually it starts at 0. We hash the block including the nonce. And then we see if our hash is under what's called the current target. And usually by under the current target, we mean that it is prefixed with a certain number of zeros. If it's not, then we either increment the nonce or change it in some other way. There are lots of different nonce algorithms. So incrementing is just a particular one, but you can also just have like a random, you can choose random nonces, you can like do the prime numbers, whatever. And then you change the nonce, rehash, and see if that's under the current target. So this ensures that the computer, that once it does find one that's under the current target, then we know that that computer has done a certain amount of computational work to achieve that hash. And we can say like, yes, you win the block. And in the case of cryptocurrencies, oftentimes if you solve a block, this is called solving a block, you get a little bit of that cryptocurrency. And that's how like cryptos are generated. Okay, so you've probably heard a lot about blockchains and security. So what kind of promises does blockchain make and what kind of promises can't it make? So because each block contains a hash of the previous block, a bad actor would need to change the data in the block, rehash it, update the next one, rehash that, update the next one. Yeah. So because of this, we can guarantee with certainty that blocks that are older than a certain amount, so usually that's like the first 4 or 5 blocks in a chain could plausibly be modified in time, and like we have the computational power to like modify and change them potentially. But after the 4th or 5th block, we can say with absolute certainty that blocks older than that were made by that user at that time with that data. What this doesn't ensure is that the data is valid. So you have to have other mechanisms in place to make sure that like I said, the data in your blockchain can be pretty much anything. And so you have to have other mechanisms in place to ensure that that data is valid, whatever valid means for your use case. We've also talked a little bit about decentralization. This also provides some really nice securities for us. It means that there's no single point of failure. So in the case of cryptocurrencies, in order to like steal cryptocurrencies from someone, I would have to do a 51% attack that we talked about earlier, where I would have to like take over more than 51% of the nodes in the network in order to falsely say, I have all this money and this other person doesn't. So it makes it very hard to steal from or like modify things in the blockchain. There's no single point of failure. I can't just run into a bank and rob it. There's also no central authority that needs to be trusted. It's just an algorithm that is deciding what the authoritative chain is, and so there's no chance of operator tampering. And if your blockchain is public, then everything is visible, everything's out in the open, and I have a little bit of security through publicity. Everything is publicly verifiable. And I don't need to trust like a regulatory body or anything like that to know that like this data has not been changed. Okay, so the question of whether a blockchain needs to be public is very controversial. I really like this quote from Wikipedia. An issue in this ongoing debate is whether a private system with verifiers tasked and authorized by a central authority should be considered a blockchain. And then there's 5 citations. So this is a very controversial topic. Proponents argue that blockchains are just structures and that there are a lot of valid use cases for private permissioned chains, and I think that there are. If you're a business and you want your LDAP to be on the blockchain, then I think it makes sense for the whole wide world to not be able to see all of your employees' like personal information. But opponents will argue that private chains don't support decentralized verification and therefore are not protected from operator tampering. So basically, if I can't trust that the data has not been tampered with, and if my blockchain is not public, then I cannot trust that the data has not been tampered with, then what I have is a linked list, not a blockchain. Yeah, words are hard. Defining terms is really hard. I don't see this getting resolved soon, but develop your own opinion and voice it. There's also many more layers to this public-private permissioned kind of I don't know if ecosystem is the right word, system. So there's a handy visualization for like all of the different kind of layers of complexity. Okay, when should you use blockchains? If you're thinking about using a blockchain, you should definitely look at Blockchain Beyond the Hype. It's a handbook that walks you through what characteristics of like use cases they should have in order for them to be good candidates for the blockchain. So highly, highly, highly recommend. If you're even considering using a blockchain, you definitely need to look at this. It's a great framework. And again, takes the hype out of the blockchain and really looks at, like, is this right for your use case? So a couple of those characteristics. If you want your data to be accurate, secure, and most importantly, immutable. So data is transactional. That means that I can have a create user and a delete user transaction, but that create user transaction will never go away. And if that's a problem, then blockchain might not be for you. You have an increasing data set, so if you're having like thousands of transactions per second, you're gonna have a really big blockchain really, really fast, and you need to be able to handle that. Your assets are digital. This is true of a lot of things nowadays, but yeah. Ultimately, this is all digital stuff, so you need digital assets to be in your data. If you are looking to remove intermediaries, that is something that blockchain is really good at taking over some of the responsibilities of regulatory bodies by having those secure promises that we talked about, primarily transactional data. And if you have contributors that don't trust each other, blockchains might be a really good solution. Okay, so voting and finance are really good. Oh my gosh, I'm so sorry. I'm leaving like no time for questions. Yeah, voting, financial sector, good candidates for both of these because we want to facilitate trust. They have a lot of those like digital aspects. We want them to be accurate, secure, and immutable. We're trying to remove the central authorities in both of these. So that makes them really good use cases. And you should not use blockchain just because it's the new shiny, or if your current technology already works, then blockchain might not be for you. Or like, don't use it just to use it. Okay, so there's lots of ways that blockchains are being used nowadays that are really interesting. So I have a little like award show called the Blockies that highlights what I think are the most interesting use cases. Originally, I had a slide that was just a list of all of them, and then that slide became 3 slides. And then I like had trouble going through all of the use cases in time, and particularly in like 2 minutes. So let's get started. Okay, the most charitable use, little drum roll, yeah, is the World Food Program. So they're using blockchain technology to record what resources people are using, so what resources they give to people, how quickly they use those resources, and then they're using that data to give more of what people need to them. And this also allows them to digitally transfer funds to people so that they can, like, without just like giving people cash, give them resources they need. The most democratic use is called Follow My Vote. And this is a little bit of the use case we talked about earlier of people recording votes and then being able to track where their vote is, what the data is, and also to count ballots and to have a much more quick and verifiable way of seeing who people voted for. The most up-and-coming use, so this is the use case that the first industry that I think we'll see like widespread use of blockchains, and that is supply chain tracking. So there's 2 main use cases here. The first is tracking expensive goods, so basically making sure that your diamonds are not blood diamonds, like making sure that your goods are coming from where you think they are. This is also applicable to like designer handbags or other places where you want to make sure that like your things are being ethically made. Or made by the people who say they are making them. And food contamination tracing. So if there's a flu outbreak at a restaurant, then we can trace like which farm that particular food came from and then where else it went after that. And instead of having all restaurants throw out all their lettuce, we can just say, no, just these places need to throw out whatever. Okay, and then the cutest use case is CryptoKitties. This is a really cute game. I highly encourage checking it out. You like breed cats, and that makes more. It's built on Ethereum, which is a cryptocurrency. And yeah, okay. there's way more, didn't cover them all. Click the links. I think we're pretty much at time. Yeah. Come talk to me afterwards, though. I'm going to lunch with my mom, unfortunately, so I won't be at the blockchain table for lunch. But yeah, definitely come find me at this conference and ask me questions. Thank you so much for coming.